Hello, everybody. So today we're going to be continuing our conversation about quantum mechanics by focusing in on this pesky little issue. Sometimes you have a wave function that isn't an eigenfunction of the property you actually care about. So we brought up an example of this last time. So cosine kx, it's an eigenfunction of energy, and that's wonderful. It means we can use it. But it turns out that it actually isn't an eigenfunction of momentum. However, most of the time, you can express almost any of your wave functions as a linear combination of eigenfunctions of the property you actually care about. So specifically, we can actually express cosine kx as a linear combination, which is another way of saying a complicated sum of the eigenfunctions e to the ikx and e to the negative ikx. And so this is essentially referred to cosine kx as being a linear combination, also known as a superposition of two individual wave functions. So I take these two individual wave functions, I go ahead and I put them right on top of each other, and what emerges, the emergent property, the superposition, is the observed eigenfunction of energy. Now, the problem is let's say I do actually measure a system to be in the wave function cosine kx. Now I have to try and determine the likelihood of the original wave function being in these two states, e to the ikx and e to the negative ikx. This is really important because this is going to give me information about how likely I am to find properties that are associated with each of these wave functions, such as the momentum. So if I know how likely each one of these is to occur, I have some information about how likely I am to find their associated momentums. So one of the ways we can try and evaluate the probability of finding the original wave function in each of these individual states is by starting under the assumption that the wave function, when applied to itself, has to equal 1. Now, let's go ahead and figure out how much of the time it's in any individual state. And we're going to do this in Dirac notation for simplicity, and you'll see why in a bit. So I can do this by applying my new linear combination of the complex conjugate of the wave function. So 1 over square root of 2 of e to the ikx, 1 over square root of 2 e to the negative ikx, both as complex conjugates and bras. I apply them to the associated kets, e to the ikx and e to the negative ikx. But remember, since these are functions, I can go ahead and use my distributive property. So I can go ahead and start by distributing out e to the ikx onto itself and then negative ikx. And the same thing with e to the negative ikx, both e to the ikx and onto itself. Now, since it's 1 over square root of 2 times 1 over square root of 2, well, that means that each one of these has a prefactor of 1/2. Now, here's where orthonormality really kicks in, because it's worth noting that each of these integrals is going to be 1, but I'm going to leave these as the combined state, just so we can see how likely I am to observe this particular combination. Now, each of these crosses, again, are equal to the Kronecker delta, but this is -1 plus 1, so they're not in the same state. So all of these are going to be equal to 0 due to orthogonality. So orthogonality is going to cancel out these two central functions. And this leaves me just with e to the ikx and e to the negative ikx. And you'll notice that I've got about a 50% probability. 1/2 of the time it's going to be in this first state, and 1/2 of the time it's going to be in the second state. So I've got a 50-50 shot of finding it in each of these individual states. And one of the ways we can kind of illustrate this is you'll notice that they both have the same prefactor. And if they have the same prefactor, it means they have the same probability. So this is a superposition of two wave functions in equal quantity, giving us equal probabilities of finding the given parts. Now, it's actually possible to essentially express this as a more general form. So I can have a wave function that is a superposition of any number of other wave functions. And so I can try and figure out how likely each of these individual states is. Now, one of the reasons why this is really important is, let's say I take a measurement. Well, if that measurement is an eigenfunction of these individual constituent parts, I'm only ever going to see one of these parts. So if these are all eigenfunctions of momentum and I measure the momentum of the particle, I'm going to see psi1, psi2, or psi3. I'm not going to see anything in between. So this means that if I have something with eigenvalues of h bar, 2h bar, and 3h bar, I'm never going to find a value of 1.5 h bar. Now, these prefactors are going to give me information about the likelihood. And we can essentially prove this by essentially showing that for a normalized wave function, the probability of being in any given state, we're going to do this for a simple two-state system. So again, we're going to do this in integral form. Again, where we're integrating over all space. And so I'm going to apply my wave function, first complex conjugate, then the actual value, just simply sum of psi1 and psi2 with a prefactor of c. So we can start with the distributive property, because again, these are just mathematical functions, so they should be able to distribute. And this gives us, let's be honest, something a little bit messy. So we have psi1 applied to itself, psi1 applied to psi2, psi2 applied to psi1, and psi2 applied to psi2. And again, here's where orthonormality really comes in. Since these are eigenfunctions, this means that they are all orthogonal. And more importantly, it also means that since we're looking at a normalized system, that means they're normalized too. So what we find is that I'm going to have a combination of psi1 and psi2. And the likelihood of finding the system in this psi1 state is going to be just c1 squared. And again, it is worth noting our prefactor can have a imaginary number in it. There is no problem with that, because if it does, we're just using the complex conjugate to get the squared. So again, the probability of finding it in psi1 is just c1 squared. The probability of finding it in psi2 is just c2 squared. So if you know what the prefactor is, turns out you can actually figure out the probability of finding the system in any given state. And this is huge, because if you're able to separate out a wave function into its normalized constituent parts, you can figure out the probability of finding it in any of those given parts just by looking at the prefactor. And again, this is a huge advantageous ability. Now, this gets even more powerful when we start dealing with what's called an expectation value. So again, let's say that like momentum, I have an operator that I'm applying to a wave function that actually isn't an eigenfunction, but it's a linear combination of eigenfunctions. So what I can then do is split up my wave function into the constituent eigenfunctions, so into a superposition of the eigenfunctions with the associated probabilities of being found in any given state. And then again, integrating overall space. So then I can go ahead and distribute the system and break it up into the individual integrals. Now, the math gets a little bit messy, but again, I'm just applying operator to psi1, operator to psi2, operator to psi1, operator to psi2, and again, with the corresponding constituent ability. Now, here we make use of the fact that psi1 is an eigenfunction, and since c1 is a constant, it isn't going to interfere. So that is going to turn each of my operators into their associated eigenvalues. So here, the operator applies to psi1, I get the eigenvalue 1. Operator to psi2, eigenvalue 2, eigenvalue 1, eigenvalue 2. Okay, this again make looking a little bit messy, but now let's go ahead and figure out what's happening here. So C1, psi1, C1, these are all constants, and all I'm left with is psi1 applied to itself. Well, that's just going to be 1. So that's nice. And I'm left with C1 squared times psi 1, or omega 1. So I'm left with the eigenvalue of state 1 times the probability of finding it in state 1. But here we have psi 1 applied to psi 2. Well, if this is an orthogonal system, that's going to be 0. So it just drops out. Same thing here where psi 2 is applied to psi 1 because, again, these are all constants. They don't matter. Now here, C2 and omega 2, these are constants. I pull them out forward. And then I'm left with an integral that for a normalized wave function just goes to 1. This means that my overall expectation value, so the overall measured property, is going to be a combination of the eigenvalue for state 1 times the probability of finding it in that state. And we can essentially sum this up in series. So if I was combining 3 eigenfunctions, I can essentially say that the overall measured or expected value is just going to be the sum of each of my eigenvalues times the probability of finding it in each of those individual states, which again can simply be obtained by how much they contribute to our overall wave function. And this is, again, a little bit messy, but a really powerful set of relationships. Now, as you'll notice, the math here, it's very messy, a lot of integrals. Let me once again express how much I love Dirac notation, because here I can express psi as just a combination of psi 1, psi 2 with the associated prefactors, which can be essentially pulled out, all applied to my wave function. So essentially what I can then do is distribute my system so that now I've got psi 1 applied to each of my individual eigenvalues times the wave functions. And then when we pull this out, we can get the same answer we did before. But here's another useful thing to note about Dirac notation, especially when dealing with eigenvalues, is what I now have here is a linear combination of equations. So I'm applying C1 to omega 1 to C1, where essentially psi 1 is associated with C1 here. So I've got combining C1 with C1, C1 with C2, C2 with C1, and C2 with C2. Now, anybody who can think way back to probably high school, but maybe you covered this in calculus, might be familiar that this fits a known established set of mathematical relationships. This is a matrix. So specifically what I have here is I'm applying a row vector to a matrix to a column vector. Now, one of the best ways to try and walk through a lot of this matrix algebra is by starting over on the right 2 variables. So what I'm doing is I'm applying the upper right term with the top term. So omega 1 C1 plus 0 C2. Well, that's just omega C1. This next one is 0 plus C1, 0 times C1 plus omega 2 C2. So that just gives me omega 1 C1, omega 2 C2. I could then apply this to my row vector. So this gives me C1, omega 1, C1, C2, omega 2, C2. This is essentially what I've just written out here, because you'll notice what we end up having is that any overlap in between, say, C1 and C2 gets annihilated because these off-diagonal elements go to 0. Now, you can also write this in our more general form, psi, omega, psi. So it's another way of looking at Dirac notation. And again, this is mostly for those of you who are really interested in the math of the thing. It turns out that a ket, or a bra, is another way of writing a row vector. A ket is another way of writing a column vector. And an operator is another way of writing a matrix. And it turns out that when you apply a row vector to a matrix to a column vector, what you end up getting out is an individual value. And that's exactly what happens when we apply expectation values. So in Dirac notation, we can find the expectation value of any operator simply through this general formula. Now, one of the other important things is that sometimes it's actually going to be important that we have to deal with expectation values if I don't have a superposition of wave functions. So again, it is worth noting at this point, our Dirac notation breaks down, but our integral notation still is useful. And one of the reasons why it's going to be useful for us to still think about superpositions, even when expectation values, even in the lack of superpositions, is because let's say I'm trying to determine the expectation value of position of this wave function in a box of L. Now, one of the reasons why this is so very important is that, as established, turns out position doesn't really have eigenfunctions. So if I want to find the average position of a particle, I need to use expectation values. So we can start by trying to find our expectation value by, again, integral over all space. So I've got a box of length L. It's going to be from 0 to L. So I apply my wave function to my operator to my wave function. No imaginary numbers, no complex conjugates, fairly straightforward. So I'm going to find all my constants, pull them out front. So square root of 2L times square root of 2 over L, pull that out front, I got 2 over L. That leaves me behind with x sine squared pi x over L. Now here we have to essentially go to our old friend, integral identities. So break out your integral table. When you do this, we find out a general solution of 2 over L times x squared over 4 minus L over 4 pi function minus a second function, and all of this from 0 to L. So yes, the math of this does get a little bit messy. But here we kind of get a little bit lucky because when I plug in a value of L, so here we have L squared over 4 minus 2 pi L over L. Well, that's sine of 0. Got it. And here I run into cosine of 2 pi L over L. This is a little bit trickier because here we have a value of 1. Oh no. Or sorry, value of -1. This is a bit problematic, but remember we subtract out the value of 0. So when you plug in 0 here, this is 0, 0. Oh, this is cosine of 0. That's +1. Turns out the L and the 0 term cancel out with this cosine expression. So all that leaves us back with is 2 over L times L squared over 4. That's L halves. Congratulations, it turns out that the average position of a particle in a box is the middle of the box. And you'll actually find this will hold for most wave functions for a particle stuck in a box of length L. The average position is going to be L. Now, it's true that we get lucky for position, but it turns out that this can actually get a little bit messier with other expectation values. And it is worth noting, you can find an expectation value of pretty much any property you can think to measure, whether it's position, position squared, momentum, momentum squared, anything you choose. Though the math does start getting a little bit messy. Unfortunately, we're going to have to spend a little bit of time with it talking about this next time as we deal with the fact that it turns out the more you know about the momentum of a particle, the less you know about the position. Next time, we're going to show exactly how the Heisenberg's uncertainty principle works. Till then, take care.